see Thevenin and Norton equivalent circuit. We are going to see an example on that. Okay, here we have the 4 voltage provider. We have a voltage source, and then we have a current source. That's a voltage dependent current source. So we are going to see, like, when we have a independent source and a dependent source, what's going to happen. Okay. So first of all, if we are trying to draw Thevenin equivalent circuit, what can we do is we can take the open circuit for this one, plus minus 4 voltage right here. And we know that why we take open circuit, because whatever the circuit you have, if you replace that one with load resistance and then Thevenin resistance and then Thevenin voltage, that's going to be the same. We just have to find out the Thevenin voltage, Thevenin resistance and Thevenin voltage, and that is what we are going to see how to do that. Okay, so this is the equivalent diagram of this R load right here, and we cut off this part of the circuit and replace that one with R Thevenin and V Thevenin. Now to find out the V Thevenin, what we have to do is we have to remove the R load and make it an open circuit and calculate the VOC, because VOC is equivalent to V Thevenin. So here I'm drawing the circuit again. This 2K right here, and then we have a voltage dependent current source right here. And that's given by Vx divided by 4000. And we have a 3K ohm resistor, and this one we leave it as open circuit. And we are interested in finding out the voltage across here, VOC, open circuit. Now here you can see this is an open circuit and we have a resistor right here. So if we have an open circuit and a resistor at this point, this resistor is going to be useless because there's no current flow here, since this is an open circuit. So I can remove this resistance and redraw this diagram. If I redraw this diagram, this is going to look like this: plus minus 4 voltage, and we have a 2K ohm resistor. And then we have the voltage dependent current source right here, that is given by Vx over 4000. And we are interested in finding the VOC. If you have VOC here, that's going to be the exact VOC at this location as well, because voltage in parallel are equal all over the place. So the voltage here also going to be the same. Okay, now let's see. Here we have 4 voltage, 2K ohm resistance. How can I find this voltage? What's the process? Seems like I can apply KVL right here, because we know this voltage and this current going through this is Vx divided by 4000. We know the current also, so we can find out the VOC. So to find out the VOC, let's apply KVL. KVL says that addition of all the voltage in summation of all the voltage in a loop is equal to 0. KVL summation of voltage in a loop is equal to 0. So if the current flow in this direction, then this is going to be plus minus right here, and then this 2K ohm resistance. If I apply Ohm's law says V is equal to I times R, and I is Vx over 4000. Vx over 4000 multiplied by 2K resistance, that's going to give us the current. That's going to give us the voltage. So multiply that. Instead of 4000, I can put 4K, so I can see the things canceling each other. And this is the current is going from plus to minus, so that's going to be a positive voltage, 4 voltage right here. That's equal to 0. That plus VOC also, because VOC also a voltage right here. So plus VOC, that's equal to 0. Now here we can see K and K cancels each other, and this is going to be 2 in the denominator. To make this one simpler, I can multiply everything by Wait a minute, wait a minute. You know what? Instead of having the like this, I had to, when I applying KVL, it's better to take a loop current like this. I'm going to erase this and redo it. Okay. Okay, let's assign the current to be clockwise, and let's call the current name as I. And if I do that, this current is going from minus to plus for 4 voltage, so this is going to be negative 4 voltage, and then from 2k ohm resistor this is going to be negative, no, plus 2 minus, because current flow from higher potential to the lower potential, so this is going to be plus 2 minus, so this is going to be a positive voltage. And we can apply the Ohm's law. Ohm's law says V is equal to I times R, I times the resistance, that is I times 2k. Then we have the voltage here, VOC. Let's put that one here as well, VOC, that's equal to 0. Now we have how many unknown variables? We have 2 unknown variables. And what is I? I is, if we express I in terms of V, like if we have a current flowing this one, and we know that Vx over 4000 is the only current source we have right here, and this one is flowing opposite to it. So if I put negative Vx over 4000, that's exactly the current I we have. So instead of this I, if I place this one negative Vx over 4000, I'm going to get one unknown variable. Because if you look at this diagram, this is like Vx, right? This is the open circuit voltage, VOC. This is the voltage we are interested in, and that's going to be the same voltage here. So this Vx actually VOC voltage. So if I replace this one with negative Vx over 4k, that's actually negative VOC over 4k. Let's do that. So this is negative 4 plus negative VOC divided by 4k times 2k, that's that plus VOC, that's equal to 0. And here k cancels each other, and then this is going to be 2 in the denominator. So if this is going to be negative 4 plus minus VOC divided by 2 plus VOC, that's equal to 0. And if I bring this 4 to the other side of the equation, that's going to be a plus 4. So we are going to have plus 4 in the other side of the equation. And then here you can see VOC minus VOC divided by 2. VOC divided by 2 means that's a half VOC. If you subtract half VOC from 1 VOC, that's going to be half VOC. So this is going to be VOC divided by 2 right here. Therefore, VOC is going to be 8 voltage. VOC is equal to 8 voltage, and VOC is the one Thevenin. That's the reason we are finding this one, because if we find out VOC, that's equal to Thevenin. So now we have the Thevenin. We found out the Thevenin. The next thing is we have to find out the Thevenin. Thevenin is going to be different when we have a dependent source and the independent source together. If we have independent and dependent source together, there's a rule says that Thevenin is equal to VOC divided by ISC. Let me write that on a new page. So if the circuit has independent and dependent sources, Thevenin is equal to Thevenin is equal to VOC divided by ISC. VOC is voltage across open circuit. That's, we already found it. That's 8 voltage. That's the one we just found right now. That's 8 voltage. So we don't have to worry about this one. But we have to find out ISC. ISC is current at short circuit. Let's find out. So what we do is we grab this circuit we have and we short circuit the load resistance. So in this load resistance, I short circuit this one. If I do that, let me copy this and paste this circuit here. I'm going to copy this and paste this circuit in the next page. Control C, Control V. Okay, here we go. Let's adjust this one a little bit. Okay, so here what we're going to do is we are just going to short circuit this R load. If I remove this R load and draw a direct line here, that's going to be a short circuit. Okay, now we have a short circuit. Now we have to, if you look at this, when we have a short circuit, what's going to happen to this Vx? Vx is 0. Like once we short circuit this one, there's no voltage, there's no Vx. So this Vx is going to be 0. So this is also going to be eliminated. So I'm going to erase this one as well. Okay, now we have one loop circuit. And whenever we have one loop circuit, what comes into your mind? KVL, because KVL says summation of voltage in a loop is equal to 0. So I'm going to just apply KVL right here. KVL and since this is the current in series, the current is going to be same all over the places. So that makes this one a little bit easier. So I don't even need to do KVL because I can directly find it, because this is a resistor in series. So we can add the resistance together. 2 plus 3k, that's 5k. So totally we have 5k resistance. If I draw the equivalent circuits for this is going to look like 4 voltage right here, and instead of this 2k 3k, I can combine them together and write it as 5k like this. And now I can directly apply the Ohm's law. Ohm's law says that V is equal to I times R. Therefore, I is V divided by R. So if I use that, I can find the ISC. ISC is going to be what? V divided by R. That's 4 divided by 5k. 4 divided by 5k is 0.8 milliampere. Now we have the ISC, and we already found our VOC. If you look at this one, this is our VOC, this 8 voltage we found before. So we can calculate RThevenin, because RThevenin, when we have an independent and dependent source, the RThevenin is equal to VOC divided by ISC. We know both of the values, we just have to plug it in. RThevenin is going to be equal to 8 divided by 0.8 milliampere. That's going to be equal to 10,000 ohm. Okay, now we have 10k ohm resistor. We found out the resistor is 10k ohm resistor. Once we have found this one, we just have to plug it right here. Now we have found out the VThevenin and RThevenin. So we have the equivalent circuit available. Now let's say if you are interested in finding the Norton equivalent circuit, how you can do that? You had to just do the source transformation for the Thevenin circuit. Okay, let me draw the circuit here first. So here I have the Thevenin circuit with RThevenin and then VThevenin right here. VThevenin, and then we have the load resistance connected like this. Okay, so if I do the source transform for the VThevenin circuit, that's going to be the Norton equivalent circuit. Norton equivalent is going to be, we are going to have the current and the resistance in parallel, and RThevenin resistance is equal to R Norton resistance. Let's put the values. We found out this 10k, and this one is VThevenin is 8 voltage, and R Norton also going to be 10k ohm resistor. We just start to find out the I Norton, and R load is going to be the right here. And I is, to find out the I, we use the Ohm's law. Ohm's law is I is equal to V divided by R. V is 8 voltage divided by 10k. 8 divided by 10k, that's going to be 0.8 milliampere. 0.8 milliampere is going to be the current we are going to have for the I Norton, and this is R Norton. This is our Thevenin equivalent circuit, and this one is Norton equivalent circuit. Okay, that's it for this video, guys. I hope you guys find this video helpful. Thanks for watching. Don't forget to subscribe my channel. See you guys on my next video.